All right, this is part 2 of mathematical statistics. And in this video, we will go over statistical operations. So statistical operations are useful measures to find characteristics of a data set. And the most common example or the most common measurement we will find in a data set or we are looking for is the expected value, also denoted as E of x or the mu of x. For people that haven't done much statistics, you can kind of think it as the average. And for random variables, we can think it as like the typical value that it will take. In other words, like the best guess. So like the previous video, we have different functions for discrete and continuous random variables. So for random variables, the expected value is given by sigma, or the sum of x, let me just erase that really quickly. So x, which is the value of the probability value of the random variable, times f of x. Fairly simple. So if we use the same dice example, we have to know that each side of the dice takes on a different value, even though they have the same probability, which is 1/6. So writing that out, we have x beginning from 1 to 6. The value of 1 has a probability of 1 over 6. Same with 2, and etc. If we add that up, that comes out to be 21 over 6, which is 3.5. So 3.5 is the average value or the expected value that the random variable will take if we roll a random 6-sided die. Okay, so for continuous random variables, again, we're using integrals because we can't find the exact probability of a single value within a continuous variable. So we're going to say the expected value is the integral from a to b, but everything else is the same. So I'm not going to give an example for continuous random variables just because they get a little more complicated as we go along. But yeah, I think the important part to know is that x represents the value of the probability, and then f of x represents the actual probability that the x can take. All right, so we found the mean or the expected value, but oftentimes we want to know how meaningful the expected value actually is, because chances are when I roll a die, or when we're finding the probability of something, it's not always going to land on the expected value. And this is the case if the data set has like a high spread or a high dispersal. If there's a lot of difference within the data, if that's the case, then the expected value wouldn't be as useful. So, and that's where the variance part comes in. It's basically, like I said, we can see it as like the spread or the difference within the data. So for discrete random variables, we can say the var of x is the summation of x minus the expected value of x squared. So subtract each value of x from the expected value of x and then square it times the probability of it. For continuous, pretty much the same thing, except we're adding the interval, or we're adding the integration. Okay, so like I said, we're not going to do continuous examples of continuous random variables, but we will do the ones for discrete, just because when we're measuring the expectation and variance of a data set, oftentimes we have a limited set of data, so we are using discrete. So let's, for a dice roll, if we want to find the variance of a dice roll, we would have to find the average or expectation first, because the variance function is based off, we need to find the expectation. It's in the variance function. So the expectation of a dice roll is given by, like I said, like we found here, 3.5. And then the variance of x, we can now find, is this 21 or 22? 18. Okay, it is 21. It's like my notes say 22, but okay. So the variance of x, we can calculate that using this formula we used here. So usually we would write out the probability of f of x for each individual x. But for a dice roll, since each value takes on the same probability, we can actually extract the probability outside of the summation, because again, each of the probability the value to take on is the same. So we can actually rewrite this as 1/6 outside of the summation, and then we'll plug in all the numbers for the dice. So so 1 minus 3.5 squared plus 2 minus 3.5 squared plus, and so on. Oops. Okay, so that value turns out to be around 3.46 or 3.47, 6 to the infinite, which is actually kind of similar to the mean. And for obvious reasons, we can compute the expectation and variance off of a computer. 99 times out of 100 we would do that, but just to get the intuitive feeling, we are doing this by hand. Okay, so a similar statistical characteristic of the variance is the standard deviation. And the standard deviation mathematically is pretty similar to the variance. Again, it is, if variance of x is denoted as the sigma squared of x, then we can see that the standard deviation of x is actually just a sigma of x. So in other words, the standard deviation of x squared is equal to the variance of x. So for our example, if the variance of the dice roll is 3.46 continuous, then we would just square that value. And then finally, a useful fact about the standard deviation and the variance is that we're always squaring we're always squaring each of the difference between the actual value and the expectation, so that the outcome of each of these measurements will actually always be positive, which means the variance and standard deviation of the result we're measuring those will always end up positive as well. So we will never get a negative value for the standard deviation or the variance. All right, moving on. So oftentimes we want to find the mean and variance of more than one random variable, since when we're analyzing data sets, we want to find the how the random variables or how the values within the data set are related. And the two most common measurements we utilize for that are the covariance and correlation. So say we have two random variables given by x and y, and we'll assume that they have the same number of values within each set. So the covariance, it will tell us the linear association between x and y, or how much x and y vary in relation to each other. We can also think of that as how x and y changes in relation to each other. So if the covariance of x and y, if the absolute values of covariance of x and y is high, then there's a close or related relationship. And if the absolute value of it is low, then there's definitely a low relationship. This is kind of a general statement, just because the covariance is always, the value of it is always relative to numbers we have the raw numbers we have in the data set. So simply giving the covariance without actually looking at the explicitly at the data set is kind of meaningless. But we use it a lot of times nevertheless. So mathematically, the discrete formula for covariance can be written as 1 over n minus 1 times the summation of the expectation of x minus the expectation of x, and then times y minus the expectation of y. So it's kind of similar to the variance formula, except we're not squaring it. We're not squaring it. We're just multiplying the difference of x and the expectation of x times the y, the difference of y. Okay. Note that this can also be written as, if this is easier for some people, and when I write it like this, there doesn't seem to be much a difference between the expectation of x times y between these two. But if you utilize the first formula, you'll see that there's a clear difference in the second as well. All right, that's the covariance for discrete functions. For continuous, we can actually write it as the double integral of the difference of x and the mean of x minus the difference of mean of y, or times the difference of y and the mean of y times f of x of y, which is actually so we can see this as the joint probability density function. So this function describes the likelihood of both x and y happening within the integral integration range at the same time. Not x or y happening, x and y happening. So that's key. All right. So the other way of finding the relationship, besides the covariance, like I said, is the correlation. Now, the correlation, in my opinion, is a much more useful statistical measurement compared to the covariance, because unlike covariance, we don't have to see like the actual raw numbers within the data set to know how close the relationship is between x and y. And this is because the correlation is a standardized measurement. It scales the covariance to values between -1 to 1. So the value of the correlation will always be from -1 to 1. And this value is made meaningful. Again, you don't have to necessarily know the values of the data set to know the relationship between, in this case, x and y. So if you see like other notes of relating to correlation, you'll kind of see it as like a slanted p, which is it's pronounced as rho. Okay, so if the value of the correlation between x and y is greater than 0, there is a positive relationship. So as x increases, and then y increases. If the correlation is less than 0, there's a negative relationship. As x decreases, y increases, or as x increases, y decreases. And then if the correlation value is around 1 or close to 1, the absolute value of the correlation, I mean, I say absolute value because it can also be close to -1. Then there's a high correlation or a very noticeable relationship, in contrast to if the correlation is close to 0. I don't know why I said rho absolute value. That's not necessarily not the most necessary, but if it is close to 0, then there is small correlation or a very, very little noticeable relationship between x and y. So the mathematical formula for correlation is actually simple once you find the covariance. The formula is the covariance of x and y divided by that's not right. The standard deviation of x. I don't know why I keep writing variance. The standard deviation of x times the standard deviation of y. So again, a lot of times when people calculate the correlation by hand, they'll forget to square root it and just use variance, which I kind of did right now. All right, so a discrete example of covariance and correlation. We can't really use a dice example in this case because there's no other data set we can use with the dice example that can be made meaningful or to find a relationship. So let's use a better example. Let's say we want to find the relationship between the amount of hours students get and then the grades they receive. All right. So in order to do that, we need to first find the expectation of x and y, find the variance of x and y, and we do that in order to find the covariance. We don't actually need the variance to find the covariance, but we do need to find the variance to find the correlation because up here we need to find the standard deviation of x and y to find the correlation, and in order to get that, we need to find the variance. All right, so the expectation of x, we can write it again, since we're measuring the number of values within the data set. We're not necessarily representing the probability. We can write the expectation of x as 1 over 5, 5 being the number of n's, the total sample size. You don't necessarily need to write a summation. We can just say that 1 over 5 times 7 plus 9 plus 9 plus 6 plus 4. Fairly simple. For the mean of x, again, same thing. Okay. The expectation of x, or the amount of hours, turns out to be 7, and then for grades, the average is 83. And then for the variance of x, it is a little of a longer process. But once you know the value of the expectation value, it's pretty simple. So 6. So the variance of the amount of hours, in the data within x is 4.5. And then I'll just write out the variance of y as well. I'll try to do it fast. 89. Okay, so doing all that, assuming no mistakes, we get the variance of 76. So actually pretty similar, a little lower, but pretty similar to the expectation once again. All right, so now the covariance. Covariance, so the reason why we subtract 1 from the covariance is, actually, did I say that up here? Yes, I did. Okay. So the reason why we subtract 1 is kind of related to the properties of the degrees of freedoms. I'll go over that later, but we are using 2 variables instead of 1, so oftentimes now we have to subtract the sample size by 1. Okay, so the covariance in this case is sample size minus 1, so our sample size is 5, so we'll do 4. And then we'll simply just plug in the covariance formula that we are given here. So this function might look a little confusing, but easier way to see this is each x value is multiplied by the same index of the y value. So 7 is associated with 82 here, 9 is associated with 89, 9 is associated with, the second 9 is associated with 94, 6 with 78, and 4 with 72. So if I write it out, I think it will be more clear. So 7 minus 7, which is 0. We multiply by the other y and then the expectation of y, and it will continually add those up. So 9 minus 7 times 89 minus 83, 9 and minus 7 again, but this time it's 94 plus 4 hours of sleep times the grade of 72 minus the average. Oh, it looks like I forgot one more. So this is 6 and then 78. All right, if we do all that, again, assuming no mistakes, it is very easy to make mistakes when we're calculating this type of stuff, but assuming no mistakes, we will get a final value of 18. So the covariance of x and y is 18. Again, this 18 right here, it's not the most meaningful because we don't know if hypothetically x and y were very big, had very big raw numbers, then 18 would actually be a small covariance. And that's why we're utilizing this 18 to find the correlation of x and y. So the covariance, again, is 18. We found out up above that the variance of x is 4.5. And then the variance of y is 76. And then obviously, if we want to find just the standard deviation of x and y, we need to square that. So we can kind of just write it in the same square root. And that will approximately give us a correlation value of 0.973. So again, what does this final correlation value mean? Well, the correlation value we got in result is very close to 1. So like I said here, because it's very close to 1, or absolute value of 1, there's a very high correlation between the amount of hours a student gets and then the grade that they receive. And then since there's a very positive relationship between x and y, it means that the amount of as this amount of hours a student gets goes up, then the chances are the grade they receive will also increase. All right, so that's it. Again, in summary, we found how to do more so discrete examples of the expectation of x, variation of x, standard deviation of x, which just the square root of the variance, and then the covariance and correlation if we want to measure the relationship within two multiple variables. If we want to do more than 2, often we need to. It gets a little more complicated. We will probably have to create it like a matrix of some sort, but 2 is usually kind of the way to go when we're analyzing data sets for now. All right, in the next video, I will go over the normal distribution and the central limit theorem. But that is all for now.